So now it's my pleasure to introduce today's speakers. I'm delighted to be joined by Dr. Himani Tandon and Dr. Kyle Gregg. Himani is a principal scientist in the research division at Optibrium. She holds a PhD in computational structural biology and bioinformatics from the Indian Institute of Science, Bangalore, and completed her postdoctoral research at the MRC Laboratory of Molecular Biology in Cambridge. Her work spans both structure-based and ligand-based design strategies for lead discovery and optimization, with a particular focus on applying AI and machine learning to model the properties of small molecule and peptide drug candidates. Kyle is a principal scientist at Optibrium, specializing in the application and development of advanced computational methods for drug discovery. His expertise includes molecular docking, virtual screening, and the integration of experimental data from X-ray crystallography and cryo-EM. With a strong focus on 3D structure-based and ligand-based design through the Biopharmix platform. He earned his PhD in biomedical science from the University of South Florida and has contributed to numerous high-impact publications on molecular recognition, protein-ligand interactions, and the development of novel therapeutic inhibitors. So, Himani, are you ready to get started?
Yes, thank you, Sophia, for this kind introduction. And thank you everyone for joining us. Before we jump into the fundamentals of QuanSA and the live demo of the new QuanSA plugin for PyMOL, Kyle and I just wanted to take a few minutes to talk about the why behind all of this today. So we all have been in that position where we, are just staring at affinity scores and trying to decide which molecules to synthesize next. But we know that numbers alone don't tell the whole story. And what if we were able to visualize what we are trying to predict? And also it often feels like that we are choosing between moving fast and being right at the same time. So let's dig into that trade-off a little bit. And I have a few questions for Kyle. So Kyle, are you ready?
Yes.
If we just look at the toolkit for affinity calculations, what do you think are the classical ways and where do they typically struggle?
So classically, we've leaned on 2D QSAR for quick screening or FEP plus when we need deep physics-based accuracy. The struggle is that QSAR is often too simplistic to capture complex biology, while FEP plus is incredibly expensive in terms of time and compute. Modern AI ML models are powerful, but they often act as black boxes that lack the physical intuition needed to generalize well beyond their training data.
I think this black box problem that you've just touched upon is definitely a massive hurdle for trust. But if the chemists who are designing these molecules know why a model is giving a high score or what the model is learning, I think they can be more confident of their new designs. So, moving on, when we talk about the practicality, how much data do you think these models actually need to be really useful?
So many big AI data or big data AI models are notoriously hungry,
Mhm.
often requiring thousands of high quality data points just to get off the ground. In the real world, though, especially at the start of a drug design project, as we all know, that volume of data simply doesn't exist. We need tools that can provide actionable insights when we have only a handful of molecules, not a mountain.
That's a nice way to put it, a handful and not a mountain. And that's the reality of early discovery, isn't it? And also, there's usually a penalty for that, right? Normally, if you have very little data, then you expect to sacrifice precision for the sake of just moving the project forward. But the question is, how do you move forward? So I think that also brings us to this question, how do we balance the accuracy versus speed trade-off in modern pipelines? Would like to know your thoughts.
Yeah, so historically you had to choose, right? The high fidelity accuracy of FEP plus at a snail's pace, or the
Mhm.
lightning speed of 2D methods that often miss the nuances of binding. Kwanzaa targets the so-called Goldilocks zone of this, delivering FEP level precision in a fraction of the time. Additionally, by using active learning, we can start with small data sets and refine the model as the project progresses, adding well-chosen molecules to improve the fit without ever having to rebuild from scratch.
That's right. So I think it sounds like we are finally moving away from, pick one or two scenarios where you can't really have speed, accuracy, and low data all at once. But I think with QuanSA, we are doing that just by marrying the best of both worlds, like the speed of the ML methods with the rigor of physics-based methods. So I think to explain exactly how the Goldilocks approach that you just said, Kyle, works under the hood, now I'm going to hand it over to you to just walk us through the core concepts. And then later, I will come back and show our newly released QuanSA plugin for PyMol. Over to you, Kyle.
Yeah, that sounds great. Thank you so much, Amani. Yeah, so to kick things off, I'll just start with kind of an overview of our agenda for today. The agenda for this session focuses on four critical pillars: an introduction to QuanSA, a deep dive into fundamentals and conceptual frameworks, the first public demonstration of the new PyMol-based graphical user interface, and a concluding session for technical inquiries. The overarching aim here is to ensure a nuanced understanding of QuanSA's capabilities while demonstrating how the new interface streamlines complex modeling workflows within the software. So I'll start with the introduction. First, I'd like to begin by addressing the inherent difficulties in predicting binding affinity, a task that remains a sort of holy grail in computational chemistry. Traditional approaches often fail because they rely on 2D representations, which are incapable of capturing the spatial orientation and electronic complementarity required for binding. Even 3D-based methods are frequently compromised by inaccurate ligand pose information or a failure to account for tautomerism and stereochemistry. One of the most profound challenges identified in this session is the limitation of existing data. Typical drug design projects rarely possess the data volume necessary to train robust machine learning or AI models. Furthermore, prospective compounds often fall outside the training data distribution, leading to the activity cliff phenomenon, where small structural modifications result in catastrophic failures of the model's predictive power. Consequently, affinity prediction fundamentally requires physics-driven domain knowledge rather than purely statistical correlation. The emphasis on physics-driven modeling is due to the correlation fallacy, where co-occurrence is assumed to mean causality. In many QSAR practices, models are selected based on their ability to correlate with a training set, regardless of whether that correlation reflects an underlying physical reality. A classic example cited in the literature involves the high correlation between lemon imports and the reduction in U.S. highway fatalities, a relationship with no causal link. In drug discovery, this fallacy often manifests when medicinal chemists design molecules based on 2D topological similarity to existing hits, creating a design bias that limits the discovery of novel scaffolds. To illustrate the limitation of common molecular representations, consider the classic challenge of predicting binding to carrier proteins like SHBG. If we use the 2D skeletal representations, molecules like dihydrotestosterone and estradiol appear very similar. They share the same steroid scaffold. However, 2D similarity is a poor choice for affinity prediction because it masks the 3D reality. As shown in the bound poses, these ligands interact with the protein in specific sensitive orientations that require accurate representation of their 3D structure, including tautomerism and stereochemistry. Ultimately, meaningful affinity prediction requires a physics-driven approach that understands the underlying physical phenomena of the binding site. In 1988, work on comparative molecular field analysis, or COMFA, by Richard Kramer and colleagues was seminal in the field of 3D QSAR. COMFA established the principle that the effects of shape and electronic properties on binding, specifically in steroids such as DHT and E2, could be modeled by analyzing molecular fields on a grid. While COMFA was groundbreaking, it suffered from severe sensitivity to molecular alignment and the choice of the grid. QuanSA represents an evolution of these concepts, utilizing the construct or utilizing the surface-guided quantitative modeling or QMOD approach to construct an interpretable physical model of a binding site known as a pocket mole. Unlike the rigid grids of the past, QuanSA employs a hybrid strategy that combines 3D molecular similarity, docking, and multiple instance machine learning to inform models of structure-activity relationships. The pocket mole is a collection of steric and polar probes that represent the constituents of the cognate binding pocket. The induction of this model proceeds through a series of automated steps that ensure the resulting pocket mole is parsimonious and reflects the actual physical drivers of binding. QuanSA is a 3D ligand-based method that achieves accuracy equivalent to FEP+, but is complementary to it. It works effectively in scenarios where FEP+ may struggle, and using a consensus between the two methods actually often yields a higher accuracy than either method alone, as shown in our study in collaboration with Steve Johnson at BMS. By using what we call causal AI, physically motivated machine learning, QuanSA can accurately predict ligand affinity even in the absence of a protein structure, requiring only a small number of active compounds to establish a robust model. One of QuanSA's greatest strengths is its ability to handle scaffold hopping. Structurally novel molecules often fall within the model's domain of applicability because it's based on 3D surface congruence rather than 2D topology. Building and applying these models is also highly tractable. A model can typically be built in hours, and new predictions are generated in seconds, enabling large-scale applications within active learning frameworks. Traditional models look at molecules 2D sketch, or how atoms are connected. If a new molecule looks different on paper, the model often fails. QuanSA instead looks at the 3D surface, the shape and electrostatic fields that the protein actually sees, and this allows it to perform scaffold hopping, identifying that two molecules with completely different chemical cores can have the same biological effect. Most AI models only work if a new molecule is very similar to the ones used for training. In QuanSA, the domain of applicability is physical. So as long as a new compound sterically fits into the 3D pocket field and matches the required electrostatic hotspots, the model can predict its activity with high confidence, even if it is structurally novel. The methodology is built for speed. A robust model can be induced in just a few hours, and once built, it can score new molecules in seconds. This efficiency makes it ideal for active learning cycles where the model quickly screens thousands of virtual designs to prioritize only the most promising candidates for synthesis. And the model can be improved as more data comes in. QuanSA is also flexible across project types. In structurally enabled projects, initial ligand alignments are informed by co-crystal structures, allowing QuanSA to fast-track compound prioritization for more expensive FEP+ simulations and complex formation experiments. In these projects, the protein structure acts as a physical anchor. So instead of having the software sort out how molecules might overlap, the protein structure defines the exact alignment. Knowing the protein structure helps the model define exactly where a molecule can and cannot go, making predictions much more robust for new diverse chemicals. In pure ligand-based projects, QuanSA enables modeling much earlier than 2D QSAR because it requires fewer active compounds. The resulting pose predictions provide critical information to guide design and save both time and cost in synthesis. This is where QuanSA provides a massive advantage over traditional 2D modeling. It allows you to be predictive much earlier in a project's life cycle. Traditional 2D models often need dozens or hundreds of molecules to find a statistical pattern. Because QuanSA is physics-driven, it can build a reliable model with significantly fewer active compounds. Even without a protein structure, QuanSA builds a 3D map of what the pocket must look like based on the ligands. This gives chemists a 3D target to design for, showing them exactly where to add groups to improve fit. So by predicting the 3D fit and strain before a compound is even synthesized, you avoid wasting weeks in the lab on molecules that look good on paper but are physically incompatible with the target. This turns a blind design process into a structure-guided one. So with that, I'd like to jump into some of the key concepts of QuanSA and really dive into it now. So on the technical side, preparation begins with SMILE strings and activity data. The SMILE strings are used to generate 3D models of all the ligands, and the activity data serves as the training data for later model building. The integrity of a QuanSA model depends entirely on the quality of the 3D data used to train it, adhering to the principle that a model is only as good as its input. This preparation phase is a rigorous three-stage algorithmic pipeline. First, we address chemical state enumeration, which is often a point of failure in 3D modeling. We do not simply convert 2D strings to coordinates. We enumerate the full landscape of tautomers and protonation states. This is critical because a protein binds a specific physical entity, and a change in tautomeric form or protonation state can completely reconfigure a ligand's hydrogen bonding profile and electrostatic surface. So by enumerating these states, we ensure the model identifies the most biologically plausible form during induction. Next, we perform exhaustive conformational sampling using ForceGen. ForceGen is a template-free, non-stochastic engine designed to navigate the low-energy landscape of lead-like molecules. Unlike random search methods that can miss key energy barriers, ForceGen uses a systematic heuristic approach to identify a comprehensive set of all relevant local minima. Grounded in the MMFF94SF force field, this process ensures that every conformer in the resulting ensemble of poses is energetically realistic. This exhaustive sampling enables the model to eventually discover the correct bound pose without requiring pre-aligned structures or human assumptions about the active conformation. We then establish the 3D reference frame through an initial alignment hypothesis. We select a small seed set of ligands, typically 2 or 3 most potent and structurally diverse compounds in the dataset, and align them by maximizing their mutual 3D morphological similarity. This process, driven by eSIM, uses Gaussian representations of steric and electrostatic fields to find the orientation where the functional hotspots of the different scaffolds overlap most effectively. This shared spatial hypothesis defines the ground truth for the rest of the dataset, providing the coordinate system that the model will use to place its observer points and induce the virtual pocket. These 3 steps, chemical state preparation, ForceGen, and eSIM alignment, provide the high-fidelity 3D dataset required for accurate affinity prediction. So by focusing on physical fields rather than 2D connectivity, we create a robust coordinate system that transcends specific chemical architectures. This preparation enables subsequent machine learning steps to accurately induce a virtual pocket grounded in realistic molecular physics. Ultimately, this rigorous front-end processing ensures that the resulting pocket field is a reliable surrogate for the true binding site, capable of guiding prospective design with high confidence. So once the ligands are aligned in a shared 3D space, the next challenge is creating a consistent way for the machine learning algorithm to observe that space. We achieve this by placing observer points surrounding the region occupied by the training ensemble. These points are not placed randomly. They are systematically generated by shrink wrapping a discrete grid around the volume defined by the active molecules. This process effectively tessellates the potential binding site, creating a high-resolution map of the specific 3D region where the protein-ligand interactions occur. The use of observer points represents a fundamental shift in molecular representation. Traditional modeling often focuses on the positions of individual atoms or functional groups. In contrast, QuanSA focuses on the physical fields those atoms project into the surrounding space. Each observer point acts as a discrete sensor that records the local physical environment, measuring steric occupancy, electrostatic potential, and hydrogen bonding capacity. By converting chemical structures into a standardized grid of field values, we move beyond the 2D topology of the molecule and focus on the physically motivated components it presents to the protein. These observer points serve as the fixed global reference frame for the entire model induction process. Because every molecule in the dataset is evaluated against the same set of spatial coordinates, the model can perform a true apples to apples comparison between structurally diverse leads. This fixed grid allows the algorithm to identify spatial hotspots or specific locations where a negative charge or a hydrogen bond donor is consistently required for high affinity. This spatial consistency is what enables the machine learning engine to recognize patterns across different chemical series that share no common atoms. Essentially, these points enable the model to view the ligands from the perspective of the protein. By placing sensors around the molecules, we are effectively mapping the interior surface of the cognate binding pocket. This inside-out mapping ensures that the resulting pocket field is a physically sensible surrogate for the actual binding site, rather than relying on abstract statistical descriptors. The model is grounded in 3D geometry of the binding event. This rigorous spatial mapping provides the necessary infrastructure for the model to later align new, unseen compounds and predict their affinity based on how well they satisfy the field requirements at each point. So once the system has placed fixed observer points around the ligand, it needs to measure the physical environment. To do this, QuanSA calculates 6 specific values at each observer point for a given ligand pose. We can break these 6 values down into 3 main categories. First, we have pure shape. This is a single value. The system simply measures the minimum distance from the observer point to the molecular surface. This tells the model about the physical boundaries and steric bulk of the ligand. Second, we look at directional polarity. This category accounts for 4 of the 6 values. For both hydrogen bond donors and acceptors, QuanSA measures 2 quantities: the minimum distance to the nearest donor or acceptor, and the angle or directional congruence of that interaction. This is crucial because a strong hydrogen bond relies not just on proximity, but also on proper orientation. Finally, the 6th value measures the local charge. This evaluates the local electrostatic field. The system calculates the potential energy required to move a fixed magnitude point charge, specifically a positive 0.2 charge, from an infinite distance to that specific observer point. So at every single point around the molecule, we get 1 value for shape, 4 for polarity, and 1 for charge. Together, these 6 measurements drive specific nonlinear response functions parameterized from the SAR data. Pure shape feeds into a combination Gaussian sigmoid curve. Directional polar measurements feed into a strictly Gaussian terms, and the Coulombic charge feeds into a learned sigmoidal curve. The model utilizes multiple instance machine learning to then determine how specific function parameters at the observer points correlate with the provided activity data. Rather than selecting one pose per molecule manually, the algorithm induces a physical pocket field by treating the collection of variant poses as a bag of possibilities. It systematically learns which physical properties at each point in space, such as a specific hydrogen bond requirement or a steric boundary, best explain the differences in potency across the training set. This process culminates in an iterative coupling of the pocket model and the ligand configurations. Through a continuous pose refinement and potential swaps, the algorithm reevaluates the fit of each molecule against the evolving pocket field. If different variant poses provides a better physical explanation for a molecule's activity, the model swaps it in and updates the observer point parameters accordingly. This cyclic refinement continues until the model reaches optimal physical consistency, yielding a robust surrogate of the binding site that accurately predicts the affinity of novel leads. The induction of a QuanSA model is fundamentally an adversarial process that utilizes the full spectrum of biological activity data to define the binding site. So while active compounds are used to identify necessary attractive features, specifying where specific electrostatic potentials and hydrogen bonding motifs must exist, less active compounds serve as a critical negative evidence. By incorporating molecules with low or no affinity, the algorithm learns the physical boundaries of the pocket, defining steric walls and forbidden electronic regions where interactions would be repulsive. This dual-sided approach ensures that the resulting model doesn't just recognize what makes a molecule work, but explicitly understands the physical constraints that cause a molecule to fail. So to ensure the model remains rooted in physical reality rather than statistical noise, QuanSA incorporates the MMFF94SF force field to account for internal ligand energetics. A significant risk in automated modeling is that an algorithm might identify a perfect fit using a conformation that is energetically impossible for the ligand to adopt. So by penalizing high strain poses, QuanSA ensures that every predicted binding mode is energetically accessible. This physical grounding ensures that the affinities derived from the model reflect the actual thermodynamic phenomena of the binding event, rather than mere mathematical correlation. The result of all of this is a continuous pocket field model that serves as a 3D physical surrogate for the protein's binding site. This model is generated by aggregating the function parameters learned at each observer point, creating a unified representation responsive to molecular shape, hydrogen bond directionality, and Coulombic fields. Unlike 2D descriptors that lose meaning outside of a specific chemical series, this 3D field effectively provides a surrogate protein pocket that designers can use to visualize and evaluate new compounds, transforming a ligand-based project into one with visual and conceptual advantages of structure-guided design. The power of this approach is demonstrated in the Kemble 315-351 case study, where the model produced prospective predictions matching experimental values within 0.3 log units. Because the model is built on fundamental physical principles, specifically the spatial requirements for shape and electrostatic complementarity, it maintains a remarkably wide domain of applicability. It is not limited to compounds within a specific training series. Instead, it provides reliable guidance for structurally novel candidates that occupy entirely different regions of chemical space. This ensures that the model remains a robust tool for prospective lead optimization, capable of identifying potent new scaffolds that a 2D biased approach would likely miss. And so with all of that being covered, I will now hand it over to my coworker Himani, and she will begin with the demo for the QuanSA plugin.
Thanks, Kyle. Can you see the screen? Just can you confirm it once?
Yeah.
Okay. All right. Thank you so much, Kyle, for setting the stage with a nice refresher of QuanSA key concepts. We have another webinar that we did some time ago that one can revisit to if you want to know more details on the benchmarking aspect of QuanSA, as well as few real-world case studies where QuanSA has been effectively applied. But for now, let me show you how we can put all the things that Kyle just explained about QuanSA into practice. And I have the privilege to demonstrate for the first time our newly released QuanSA plugin for PyMOL. So this is what the plugin looks like. And in this first window, I mean, you can easily install the plugin through Plugin Manager. The instructions are pretty straightforward. And in this window, we can define our project title, the directory name, and the location where we want to save this so that all the files that are generated as part of the modeling process can be saved at one location and one can refer to it at a later point. So we can just create a project. And in this demo today, we will be actually building 3D quasar models for predicting the binding affinity for the ligands that target CDK2, a very well-known serine threonine kinase, well-studied, important drug target, and it has a lot of data available. So the predicted affinities and poses that come out of after QuanSA modeling, we will analyze them and I will demonstrate the effectiveness of QuanSA method in guiding the new designs. So we will first use the QuanSA's capability to import the ligands, split the data into training and holdout sets, generate those initial alignment hypotheses that Kyle just explained about, and then build and refine the QuanSA models and predict the affinities for the molecules. So the first step is to import the molecules. So QuanSA basically supports different formats. You can import your molecules in STF format, SMILES format, in a CSV file as simple as that, which has your structures in 1D or 2D and the associated activity data with it. So and then once we have that, we can just click on the file that we want to select And it'll ask a bunch of questions for you to confirm whether your data has smiles or any other format. And then if you want to import the activity data as well, which you would like to, and then once you click yes, it would do, I'm sorry, I think I should select another molecule, this one. So once we have imported it, it would do a sanity check of the molecules and then, automatically identify the fields. And then once you click next, it would just do another sanity check for the names and everything. And once you have that, this is the main step which would be used to create those conformational ensembles that Kyle was talking about, that QuanSA uses multiple instance machine learning. And this is what is the crux of it, that it doesn't just start with a single conformation, but rather an ensemble of conformations to try to fit into the model that it is learning, the pocket field model. So here we would define all these parameters and we choose the pQuant level of conformational search mode, which is our deepest level of search mode that generates up to 1000 conformers for every molecule. And if your data set has stereochemical centers and if the chiral centers are specified in the smiles itself, it would respect it. Otherwise, you can ask QuanSA to enumerate chirality for you. And then you can also use any torsional constraints and things like that during conformational ensemble generation. And once I click next, it would just start running. It would enumerate the conformers. And for a data set of about 80 molecules on a 10 core Mac laptop that I'm using, it takes around 5 to 8 minutes to import these molecules. But of course, I would not want to wait for it for now. So I have them already prepared in another session in QuanSA, which I'm going to show you now. So after the processing and the ligand preparation step is complete, you can see that the molecules are now listed here with all the activities and the number of conformers that it has generated for every molecule. And we can actually start exploring it. So if we look at this molecule M80 here, this is the structure. And if I want to look at the whole conformational ensemble, I can just enable it, load it, and then see that this one has 102 conformers enumerated. And if I go to the next molecule, which has visibly more rotatable bonds and is more flexible, and if I load the conformational ensemble for it, we can see that it has identified about 950 odd conformers for this. So once we have prepared this conformational ensemble, we are now ready to go to the next step of model building. And the model building starts as, if you remember just now, Kyle talked about the flowchart, that it starts with the input structures along with the activity data. And the first step in model building is generate those multiple structural alignments. And these alignments form an important part of a model induction process. And we would like to ensure that these alignments are visibly correct. So we can click on the build new models. The first step that QuanSA would do is to split your data into training and holdout set. There are different strategies that you can use. Here I'm using the strategy to split about a third of data into training and the remaining data into into holdout. Another thing that the plugin also shows you is the range of activity distribution amongst your training and holdout set, and you can actually see what's the number of compounds in each activity bin, as you can say, for your data. And this is just to ensure the equal representation of your compounds in training and holdout set for a good model building. At this point, if you are very sure you want to keep certain compounds in your training set, you can actually move them up and down. And once I click next, this is the step that actually helps you control the aspects of multiple structural alignment that will be performed by QuanSA. So by default, QuanSA produces 5 different multiple structural hypotheses. You can change that number, and all these hypotheses would be used to induce a different QuanSA model based on the activity data. Now, at this point, again, referring back to what Kyle explained in the presentation about that if you have some ideas about how your compound binds to the protein, if you have structurally enabled project, then you can use that co-crystallized ligand to guide these structural alignments to have more confidence. And in this case, for example, I'm going to use one of the crystal structure for one of the inhibitors in my data set to guide them as to guide the alignment process. Now, again, once I click next here, the alignment hypothesis process would begin, and it would take around 5 to 6 minutes again on my laptop to generate 5 different alignments for this data set. With this, I again have all these hypotheses loaded here to show you. As I said, we have 5 different hypotheses. At this stage, we really encourage our users to, go and really have or analyze these alignments to make sure that they are coherent and there is nothing worse about these alignments. So you can actually scroll one by one to these hypotheses and then just make sure that all of them look good to you. And for example, in this case, because these all ligands bind to the hinge region of the CDK2, you can actually see that the hinge binding motif is quite nicely aligned on top of each other. And you can see that variability lies mostly on this left-hand side region of these molecules. And the right-hand side regions, again, are very nicely aligned. So all of these alignments in this case look reasonable and can serve as a good starting point for model induction. At this stage, you can, as I said, if you don't like a hypothesis, you can discard it, and that will not be used to generate the or induce the QuanSA models. Again, at this step, once I click next, it would start building the models. And again, for this data set, which has about 56 odd molecules on my laptop, it takes around 1 hour, 10 minutes to build 5 models. Run the 5 models against the holdout set and give you all the statistics of the models that I'm going to show you in a second. So that's really, really fast, if I would say, and it can start building meaningful models with small amount of data as well. So now, if once the model building process is complete, you would see these 5 models listed and their corresponding statistics associated with every model. So again, these are training reports and holdout reports that actually one can click and view in this viewer here. And this is again to make sure that model training has converged properly. So what we go is to look down at the training refit statistics, which basically talks about the model convergence parameters. And we also look at something called as parsimony. We are looking at models that are highly parsimonious. And by default, QuanSA plugin highlights the model that has the highest score when combined across the holdout set and the training set. What we also look at is the average error of prediction, the correlation in terms of Kendall's tau for both training set and holdout set. And this is how we can make judgments about which model we want to use for further refinement or use them for predictions for activities of the new molecules. And as I said, we can explore all these models. By default, the best scoring model is chosen automatically. Now, let's come back to the crux of seeing how we can actually visualize what QuanSA models have learned. So again, touching back on the aspect of black box thing that we were talking about at the beginning of the webinar, it's always very informative to visualize what the model has learned, and if we can understand what makes a molecule as active molecule and what makes it as inactive molecule, so that we can use that information, say during lead optimization, to guide our further designs. So in this case, once, of course, from the previous one, once the model building is complete, you can actually see all these molecules listed here. And I'm going to show you actually 2 molecules from the training set, this molecule M01, and which has an activity value of 4.2 in PKD terms. And I'm going to show you another molecule, which is basically about 1.7 times log units more potent than this molecule. And this is the best thing about, QuanSA that I personally really appreciate and find it really, really useful when I'm building affinity models, is that I'm able to visualize what interactions this ligand is making or it has learned to make with the induced pocket field from the set of training ligands. So in this case, for example, we can actually, the plugin allows you to visualize this in a very nice graphical way. And in this case, what we can see here is the overall surface, the shape of the molecules that Kyle was just talking about, that what QuanSA models learn and the properties that it learns is the surface properties. It has hydrogen bonding donors, acceptors, and electrostatic potential properties that it learns. So in this case, the cones here or the sticks here that you see in cyan are the hydrogen bond donors. The red cones are hydrogen bond acceptors, and the surface patches that you see here are the steric or shape complementarity interactions that contribute to the affinity score. Now, in this case, we can see that for these two molecules, the hydrogen bond donors and acceptors, especially in the hinge binding region, hinge binding motif, are exactly identical for these two molecules. But what makes the one molecule more potent than the other are these additional steric interactions that these two components here are making with the pocket field. So I think we can appreciate it more if I just hide the surface of the second molecule, and you can see all these happy interactions, steric interactions that the second molecule, the more potent molecule, is making with the pocket field, which QuanSA has effectively learned. And I think this is very, very powerful and useful information during our design efforts. Now, another thing that I really want to show you is, we've already discussed that QuanSA is a ligand-based method. It does not really require a protein structure to effectively build the pocket fields and learn what interactions a molecule is likely to make in the pocket field. But because for this particular example, we do have a lot of co-crystallized structures available and we know how the ligand binds, if I just bring that structure into this frame of reference and highlight the residues that bind these ligand molecules, I think it's really interesting to see how QuanSA has learned that information only from the ligands and the structure activity data. So these cyan residues are the hinge residues from the pocket, and these yellow residues are the other residues that bind to other parts of the ligand molecule. But in this case, if you can see, then the hydrogen bond donors and acceptors align really well in the pocket. So wherever the ligand has a hydrogen bond acceptor, the corresponding residue in the pocket is a hydrogen bond donor. So this is something, again, is very powerful, and QuanSA is able to learn that information. Again, it's worth mentioning, without the presence of a protein structure. So at this point now, once we have looked at the what model has learned, we can now start looking at how it is making those predictions. So let's look at the holdout set first. And we can actually now see how it has made predictions. We can copy these predicted values and compare it with experimental values in a scatter plot, and we can see that QuanSA is able to get very less average error for this case, and it is able to predict accurate values for the holdout set. Now at this point, we might want to directly use this model that we have generated to make predictions for the new molecules or molecules for which the activity is not yet known, or we can design an active learning strategy where we can choose some of the molecules from this holdout set to refine the model. Again, this is one more thing which we touched upon a little bit in the beginning, as well as Kyle explained, is about active learning. In this case, you don't have to rebuild your models from scratch when new data becomes available. Rather, you can just choose some of the molecules that are informative and can just add to the existing model to refine the model predictions. So for example, in this case, if I just choose the molecules that are predicted to be most active, and I decide I want to refine my model with the top 5 most active predicted compounds, I can just choose this in the plugin and then see how they align with the molecules in the training set, and then just click on refine the model. So what this process would do, it would just add these molecules back to the model and retrain the model. And after that, because again, it would take about 20 minutes to refine the model. So we can go back directly now to what I already have saved for you. Once the model process is complete, you would see another model that gets populated here, which would be called model 1.1. This is because I decided to refine the model 1. And once you have it, now you can actually see that the training set has 59 molecules as compared to the training set of the previous model, which had 54 molecules. And now we can again go back to the predictions and start analyzing how the model is making that prediction and what factors contribute to the activity of the molecule the most. Another thing that I want to mention is that the size of these sticks and the patches basically correspond to the importance of those features towards the activity of that molecule. And as you can see here again, there are additional interactions, hydrogen bond acceptors and donors that this molecule is likely to make in the pocket field, and that's why this molecule is more active. It's predicted to be more active. Now, at this point, this was all about the training and validation of the model, but the main task is how we use these models to predict the activities of novel compounds. Now, at this stage, you can actually, once the model is created and you have chosen the model after refinement, you can go back to the inputs tab and import the molecules again. For example, in this case, the new compounds that you want to predict activities for, again, it would ask you a lot of questions. And then once you select it, you don't want to import the experimental activity data because you don't have it. I'm not going to import it right now, but once it imports, it again calculates all the conformers, possible conformers for these molecules, and it would list this under this panel where you don't have any activities and you want to predict the activities of these molecules. So again, we can go back to those models, go to this tab here. These are the 4 compounds for which we don't have the activities yet and we want to predict it. We can just select these 4 and click on predict 4 molecules. The predictions for new molecules just take second for every molecule. And after that is finished, this is what, again, the results would look like. It would populate the predicted activities, and you can now go back and start comparing what makes a molecule likely to be active as compared to another molecule which has low or less activity predicted. And again, in this case, we can load back the interactions visualizer again, and we can change the representations if we want to, depending on how you would like to see these visualizations. Change the color of it, representations, you want single color, double color. And again, we can look at what contributes most to the activity of these molecules. And again, in this case, if I just delete or disable the steric component of it, we can clearly see what makes a compound more active than the other. So I think this is what I wanted to show you about the this newly released QuanSA plugin. And we would be really happy for you to try this out. And at this point, I think we can go back to the slides. And if you have any questions, we would be happy to answer those.
Thanks, Himani. Thanks both for the presentation and demo. If you have any question, please add these to the Q&A panel at the bottom of the screen, and we will work through as many as we can with the time left. So I already have a few questions for you both. So the first one is, how many molecules and what kind of assay data and activity range is required to build a QuanSA model?
I'll let Himani answer this one.
Yeah, I can take that question. Sorry, I think the question is about how big of a data do we need to generate these models, right? So yeah, as we have been saying that at the beginning of the project, we generally don't have a lot of data. So QuanSA models can be effectively built with as low as 20, 25 molecules, given that you have some diversity in the compounds and some diversity in the activity that you have. Of course, those models won't be perfect, but you can actually quickly climb up and use those models to screen large libraries and then keep refining them in an active learning iterative manner to get more meaningful models.
Thank you, Himani. So the next question is, how can QuanSA be deployed within my workflows?
Well, like we
You want to
said,
take this?
yeah. So like we said, QuanSA is a very flexible piece of software. It works in both structure-based workflows and ligand-based workflows. So I'm not sure specifically which ones you are implementing, whoever asked this question, but yeah, I think it fits within just about any project, especially because it can be used so early on with, as Himani already just pointed out, so few molecules to really, build that initial model, and then it can just be refined as you move along within the active learning cycles. So I think you would be hard pressed to find a sort of place where it couldn't fit into your workflow.
Yeah, I think I just, to support what you were saying, Kyle, I just opened the slide that you also discussed about the ligand-based applications and the structure-based applications. So I think it's this is very, very flexible application.
Thank you. Thank both. So the next question is, can QuanSA handle stereochemistry and learn activity cliffs around stereo centers?
I think Kyle would love to respond.
Yes, it absolutely can be used for that. That's kind of where we feel it truly stands out, particularly against other QSAR methods and affinity prediction methodologies. Yeah, it can definitely be used in this way since it's physics-based, and it's using all that information that we talked about, the electrostatics, the hydrogen bond donors and acceptors, and as well as the steric interactions. It takes all of that into account, and it's constantly, as I said, it's when you're inducing the pocket field, it's iteratively going back and adjusting the alignments, and so it's this sort of adversarial process as I described it before, where it's improving itself and it's checking and making adjustments and swapping in new confirmations as things make more sense as it's comparing to the activity data that you provide it.
Thank you. The next question is, how well does QuanSA performs against FEP+?
Yeah, so oh, sorry, go ahead. I'll let you take
No
it.
worries, you can take that. But I think you've already mentioned this as well during your presentation, Kyle, that we have benched QuanSA against FEP+, and what we have seen is that QuanSA performs equally well as FEP+, and in fact, its application is not just in structurally enabled projects, but also when you don't have a structure available, target structure available, and you can't really apply FEP+ like methods. And as well as in cases where you have, scaffold hopping, or your data is too diverse. So in those cases as well, QuanSA works really, really well. And just to point again, we have published some benchmark studies, which I think we have referred to during the webinar, and we'll be happy to share those resources as well.
Yeah. And just to add to that too, I mentioned this during my portion of the presentation, but if you do have FEP plus and you're looking for that sort of final polishing step, you can use QuanSA in conjunction with FEP plus, because the affinity predictions provided by both are uncorrelated. You can actually combine them and increase the accuracy, which we've published that benchmark as well in a collaboration with BMS. It's a really good paper, and I strongly encourage anyone to read it.
Thank you. So the next question is, how QuanSA understand that where group or atoms needs to be extended without having protein structure?
Yeah, so for this, I think, again, referring back to Kyle's presentation, he was mentioned about the placement of observer points. And that's really the deal that actually helps QuanSA learn the features of the molecular surfaces, because what observer points really do is that they try to look at the molecules how a protein would look at them on their surfaces. So you don't really need to have the protein structures, but those observer points act as a proxy of the protein pocket around the set of those ligand molecules and the envelope. And it is from those observer points the response functions are induced, the hydrogen bonding donor potential acceptors, and then electrostatic potential and the overall shape.
Thank you. The next question is, have you ever taken or have examples where the results from a screen, for example, HTS or something else, through QuanSA to predict what the next best compound should be made or followed up on? What were the results?
Yeah, I think this is the most common application of QuanSA that when we work with our customers, we routinely apply it, in such scenarios. And I think QuanSA has been extremely helpful in for people to, choose the next set of compounds. So there are various quality metrics that QuanSA provides in terms of confidence, domain of applicability, and the predicted score, which can be combined in a meaningful way to actually prioritize and rank order your compounds. And we have seen really working closely with our customers that the designs and the enrichment if I can say in that sense, is really, really high.
Thank you. That's all we have time for today. Any question we don't have time to answer, we will try to follow up via email as soon as we can. Details of our next webinar will be also available on the website and LinkedIn page shortly, along with other helpful news and information to help transform your discovery. All that's left for me to do is thank Himani and Kyle for an insightful talk. Thank you all for coming, and we'll see you next time. Bye for now.
Hi, thank you so much.